Well, welcome everyone. Thank you very much for joining this BSG seminar on the subject of cliff retreat and its landscape significance across 3 orders of magnitude in time and space. My name's Ollie Burns. I'm a geomorphologist at the Environment Agency in the National Geomorphology team. I am in a job share with my colleague Nish Halwin at Natural England as the regulatory representative on the BSG's Committee for Professional Geomorphology. So Nish is also here. Also from that committee, we have Hannah Joyce from Atkins Realis, who's the consultancy rep, and I'm going to be chairing, and Nish and Hannah are going to be making sure everything's running smoothly behind the scenes. A few sort of housekeeping bits and pieces first. This session is being recorded, as you can see. Later on, I will allow you all to unmute and put your cameras on if you wish, but please bear in mind that your questions will also be recorded, and the plan is that this will be hosted on the BSG's YouTube channel at some point soon. Just before I introduce our speaker and we kick off, a few words to say about becoming a member, in case for those of you who aren't already members. The BSG provides contact with a worldwide body of geomorphologists. It gives you some fantastic networking opportunities with a range of both academics and professionals in industry, as well as opportunities for postgrads and in overseas contacts too. Through membership, you get access to the Society's journal, Earth Surfaces, Processes and Landforms. Get regular electronic newsletters, which have got a host of useful information in them. And you'll get access potentially to a number of grants for things like research, conference attendance, field trips, and so on. There's a range of online and web-based resources as well, and opportunities to take part in workshops, CPD events, field trips, that sort of thing. So it really is worth your while if you're not already a member to sign up. Right. I'm going to stop sharing that, and I'm going to introduce our speaker for the day. So I'm delighted to welcome Dr. Uwe Dornbusch from the Environment Agency. Uwe is a senior specialist in coastal environments at the Environment Agency. He studied geography at the Freie University in Berlin, with his studies initially focusing on alpine environments. So he wrote his dissertation on the glacial history of the valleys in Tyrol, Austria, before undertaking a PhD on the extent of the last ice age in the southern Peruvian Andes, building on fieldwork from the 1950s. Uwe had a brief stint as a secondary school teacher in Berlin before he took up a short-term lectureship at the University of Sussex, which led to 6 years of Interreg-funded postdocs on erosion of chalk cliffs and the changing beaches in southeast England. He had a brief stint as a coastal engineering consultant before switching to the Environment Agency in 2009, where he's produced a steady output of papers and conference contributions on hard and soft coastal issues, often focusing on changes in southeast England and how these relate to coastal management. So Uwe, thank you very much for joining us, and I will hand over to you to share your slides.
Okay. Well, welcome everyone, and good afternoon. I hope you have something nice to eat in front of you. So this is a very academic title, and I thought that might entice some people to dial in. But obviously, this being the professional geomorphology, we like sort of have clearer questions. And so fundamentally, it boils down to where was the coast and where will it be in the future? And even that is sometimes a bit long. So we're really interested in future erosion rates, because that will impact how, for example, the planning system addresses the question when. When will the house fall into the sea is, in flood and coastal erosion risk management, basically the fundamental question. So how do we look at this? Well, there's the past and there is the future. So past, fortunately, goes out into the seaward direction as well. So there's time and space substitute. And as we go closer to the shore and as we got closer in time, certainty of measurements and anything else increases. And as we go forward in time, certainty decreases again. And I happen to call this the certainty space-time continuum, because it's 40 years back to the future, showing my age. But this looks all very nice and straight, and I don't think it is that nice and straight. I think it looks more like that. Adding some methods to this, UAV LiDAR area photography, they all provide the same certainty in terms of timing and in terms of precision of location, but obviously they cover different lengths of time. Going back further in time, you get to the OS maps, and they are sort of, well, slightly less certain, largely because you don't really know exactly which year it was they were doing it. You don't really quite know what they did, and so it's not quite as good. And then as you go even further back in time, as far as you almost want, it's cosmogenic radionuclide geochronology, which in itself is probably it's great. I mean, for glacier and deglaciation, I think it's marvelous. The difficulty is on the coast, there's lots of variability that takes place and that you really don't know anything about it. So rigorous numerical modeling might be quite difficult. Looking forward, you can obviously extrapolate, and the good thing about extrapolation is you can do that for however long you want, but do you actually have any information about what it was in the past that you can reasonably confidently extrapolate? Processes model, well, there are a few around, but again, one of the difficulties is, well, can you calibrate it? And for most of the coasts, where, for example, defenses have been in place for the last 150, 200 years, you don't really have anything to go by. You may have to resort to a conceptual model or the more democratic version of that, an expert geomorphological panel, creating an assessment. And somehow we'll cover all of this, jumping backwards and forwards in time from site to site, and everything is happening in the southeast of England. So, simmering, niggling background. So the things that rumble around your head for decades to go is this slide. So you start off with cliff retreat of the chalk cliffs in East Sussex. Now, in front of them, there's flint, gravel, beach. So how much do these produce? Now, once you work out what the percentage of chalk is in of flint is in the chalk, you can make some assumptions saying, well, okay, there's about 5,000 cubic meters of flint shingle produced every year. Now, how does that compare to assuming that, for example, we assume the same retreat rate as is in the past over 5,000 years, and that results in a volume produced of about 0.04 cubic kilometers. Now, how do I compare, or what do I compare that with? All the active beaches in West and East Sussex contain about 0.025 cubic meters of gravel and shingle. Difficulty is, so that would actually work, but the difficulty is it would require a lot of westward shingle transport, which hasn't really happened. So those 0.04 cubic kilometers don't actually contribute necessarily to the 0.025. Dungeness, on the other hand, which sits to the east of the cliffs and therefore downdrift of the longshore transport, contains about 0.2 cubic kilometers of shingle. And all that shingle arrived largely over the last 6,000 years, and quite a lot of it actually arrived in the last few thousand years. So the natural shingle along the Sussex coastline is essentially a fossil deposit and not produced of cliff erosion in the Holocene. So all that shingle that is in Dungeness, where was it before it arrived at Dungeness? And that is sort of a fundamental question that actually ties in with the cliff retreat that I will talk generally about in this presentation. Now, some idea as to where that might have been was in a presentation in 2006 by Simon Jennings. I saw this at a conference, and basically he studied the estuaries of the Sussex coastline and determined when they were closed and when they were open to the sea. And they alternated, basically, which means that some mechanism, and in this case, he postulated that it was the beach, moves across them, closes them up, and then they open up again. So probably the beach came from the west. Now, similar niggling background too is 20 years ago, and I've seen Cherith is listening too, so shout out to Cherith Moses. We looked at cliff retreat and through time and how it developed. And the crucial thing is that this is the rate from 1873 to 1973, and this is the rate from 1973 to 2001. And it drops quite dramatically, the reduction in cliff retreat. And you think, well, why is that? But also, for how long had it retreated at that rate? Now, we're looking slightly more in detail at Seaford Head. So the rate to remember is 0.3 meters per year. And I'll mention that a number of times again. So going back in time and looking at cosmogenic radiation, that's a great method because it just measures how much accumulates in the rock in terms of isotopes, 10 Be, for example. But the difficulty is on the beach that you have water coming in and out that shelters and protects or shields the radiation from the rock underneath. You may have a beach or sediment cover at some point in time. You have the shore platform that is actually eroding downwards, so you're losing your most the layers with the most concentration. You're losing all the time as the erosion takes place. In addition, the assumption that at time one, basically at the start when sea level rose during the Holocene and came in reach of the cliffs, you didn't have a vertical cliff. You had a cliff that was leveled through subaerial erosion or subaerial weathering, and you had a sediment cover in front of that because you had whatever 80,000, 100,000 years of periglacial activity. If you were lucky and the cliff surface, so the land surface behind the cliff is actually rising, then you had lots of periglacial slope deposits that run over that subaerial deposit as well. So there's a lot of stuff that you have to A, go through with your erosion, and B, there's a lot of shielding taking place here in areas that you may encounter still on the shore platform. And then as sea level rose, you could have a beach developing, coming along and disappearing again, but that is completely unknown, so rather difficult to monitor. And then you may have actually starting point that in the starting point, you don't just have all the sediment that sits in front of it. You might have had a shore platform that sits a lot higher than the one that you assume. This picture is a postcard from the early 1900s and shows the cliff at Brighton Marina. So there's now a big marina in front of it, but you can still see the top of the shore platform at the splashed wall behind the seawall. And the white is the chalk, and there's a vertical cliff there. In front of it, there's a little bit of shingle beach. But that platform sits about 5 meters higher. All this brown stuff is a bit too red. It is slightly more yellowish, but that is what I said, these slope deposits. Now, the cliff comes out here as a vertical face. So where was that during the last interglacial, for example? How does the geometry of the cliff work? So knowing when and at what position this cliff here, which is east of Brighton Marina, started, is almost impossible to know. Now, I don't go through all of this, apart from that this is one of the measurements were taking place at Seaford Head. And the result of that paper, which is actually quite interesting, says that 2 to 6 centimeters per year prevailed for most of the Holocene in terms of cliff retreat. Now, most of the Holocene is the good question. Well, so when did it start? I mean, most of the Holocene is at 10,000 years, or is that 5,000 years? But assume that is the rate that happened before there is the historically observed one from the maps. Now, Seaford Head, this is the first edition OS map from the 1870s, shows, well, coastline basically. But it also shows here something that's labeled as the Roman camp. And down here we have the start of a small, dry chalk valley that usually you would sort of ignore, but they become quite prominent because you can find some of those in historical maps. This is the start of the dry valley, and the footpath is still behind it, just like in 1870. Now, in historic maps, you find something like that. So there is the castle labeled here, and there's another castle here. But obviously, you look at the maps and you think, well, I don't even bother putting them into ArcGIS and try to georeference them because they will be kilometers out, and they are. But then someone sent me some maps, which one on the left-hand side is from 1624, and one is from 1764. And they are estate maps. So obviously, the Duke of Newcastle had some interest to know what size the parcels of land were that he tenanted out to farmers, because he basically wanted money for them. So those maps are probably quite good. Now, this one contains this castle area. Now, this one contains that little start of the valley, in addition to some other aspects of it. Now, if you put that into ArcMap and georeference it, and you find 28 points of coincidence between that map from 1624 and either historic maps or aerophotography or LiDAR or so, you come up with an RMS value of 16 meters, which actually, in the greater scheme of things, is quite remarkable. Given this is sort of vellum that it has shrunken and expanded over the years, probably. So that's great. Just as an example, you can see here, there's the Hangman's Way, so obviously a path, and that path seems to continue along that line here and goes basically off into Cuckmere Haven. If you just put a line on this, overlay this with a recent sort of OS map, you see, ooh, this does actually coincide reasonably well with what there is. If you just focus on 4 control points near the coast, well, then you get an RMS of 2.9, but that might be just lucky. Now, if I go back and have the historic retreat rate of 0.3 meters per year over the 250 years that this map precedes the OS mapping, I would need to see 75 meters of cliff retreat. Now, just before I show you that, I look at something else, because historic interpolation or interpretation sometimes is a bit misleading. So this is called on maps the castle, the Roman camp, but actually is a bowel, barrow, or hill fort from the late Neolithic. And this is basically the embankment, and in front of it there's a little ditch which is largely infilled but was excavated. Now, in 1877, someone saw this and thought, well, the destruction of probably at least one half of this camp by the erosion of the cliff by the sea must be the reason for why this looks so odd. And this has been taken forward even by historic in 1996, basically saying that this has been severely eroded. Now, this assessment results from, there's loads of those hill forts in the country, and most of them, or almost all of them, are inland, and they are circling as a contour a little summit of a little hill. Now you wonder, why would I go to the coast and look for a hill that stands sort of isolated so that I can build a complete ring around it, when there is one? Well, I don't actually have to dig that much out, because at least a large percentage is cliff, and so that's nature doing it for me. So working with natural features, basically. However, if you assume sort of, yeah, well, it might have been double the size, and you say, well, this is 500 meters. So if I divide the 500 meters in the other direction by 0.3, I come up with 1,666 years. This just fits reasonably well. It's only half the time that would be from the Neolithic. So it is possible. But now comes the comparison between these maps. And fundamentally, the map in the background is the one with the 4 ground control points, and the line that you can see, the black line, is the one with the 28 control points. You can also see a little bit of LiDAR data, which tracks a fossil cliff from the slope, and which also tracks the outline of that camp feature or castle or fort feature. And you find, well, they actually are quite close together. So the geolocation worked reasonably well. Now, if I add 75 meters in front of the white line, which is the 1872 cliff line, I see that 1624 coastline cliff line was nowhere near that. It was actually pretty much within the boundaries or uncertainty of that old map. So I reckon the cliff actually didn't really retreat at all between that time. Now, the same can be done, and I don't go through it, for the other map on the eastern side of Seaford Head, but just highlighting sort of how you get the corner of the 1873 line map with that little feature nicely colored in of the start of that little dry valley. And because the work in the past had been done until 2021, and there's 20 years later, you think, well, I might as well, because it's easy to do, plonk the photos into Agisoft Metashape and do an SFM analysis and get really good cliff lines out of that. So the result of that is that you can, based on previous work, you divide the coastline into 50-meter sections, and you calculate basically the retreat or the position of each of these for the various time intervals. And so the main thing is the western side of Seaford Head here. So in different locations, that cliff line either coincides with the horizontal line, which is the baseline from 1873, or it is a little bit further down, but there's nothing like 75 meters to be seen. And similarly, the one for the eastern side of Seaford Head, although it's only 100 years before the OS map, but it still shows very, very little in terms of variation, and that there would have been any cliff retreat taking place at that time. Now, if you sum these up and you put them in a chart and you find out that this is the western side of Seaford Head, you have an average retreat rate of about 8 centimeters. And for the eastern side of Seaford Head, you would have one of about 5 centimeters. And that, to some degree, coincidence or not, fits sort of reasonably well with what Hurst et al. Found from the cosmogenic nuclei, which is interesting. Also, just to highlight the deceleration of cliff retreat that I mentioned from the table before. So adding another 20 years, you see everywhere erosion rates are going down. And the question obviously is as to why. So the question is, when did the cliff start retreating? And when this was not that long ago, why? And the answer is woods. Now, forests. This is a forest at Cliff End, fossil forest from about 5,000 years ago. You can see in aerial photography the tree trunks lying around when they're not covered by sand or whatever. You can see them on the ground lying around in a sort of matrix of clay and mud and probably some peat. Very quickly, obviously, jumping from forests briefly to beaches again. The beaches have just moved landwards. This is from about 9,000 years ago at a water depth of 20 meters, Mellet and al. This is a dredging site, and so therefore lots of geophysics was done, and they worked out that it's basically just a sequence of shingle ridges that move gradually landwards. And they will have moved so gradually landwards ever after. and you would have at some point, say 4,000 years ago, ended up with a gravel barrier sitting at pretty much the same water level, sea level, as it is now. Why there is so much flint, and this is a really old animation, at least 20 years old, showing the pink is the chalk, and you see the rising sea level with the Flandrian transgression. And most of the chalk is actually on the north side of that channel. That's why the English coast is blessed with lots of shingle, and why the French coast doesn't have that much shingle. So there's a lot of supply from the periglacial weathering that could have been brought up. Now, going back to forests. In 1814, in the Gentleman's Magazine that I was perusing at some point, came across an article that says, there are the remains of 200 or more trees just above low water mark. In 1850, similarly, large stumps and horizontal position trees 20 feet long, which all looks like what we see at Cliff Endwith up here. There are at least 3 other sites along this stretch. Most of them are no longer visible. The only one really good site is at Cliff End, but we have some historical accounts of those. So this again is from Mellet and their model of having the gravel barrier sitting outside where from or offset quite a bit from the present day coastline. And here we have an example for how the shingle arrived at Dungeness, basically. And over the last few hundred years, this is Rye Bay. Rye Bay was filled in with lots and lots of shingle. And that must have come from somewhere to the west. This point is where the fossil forest is, to which I will take you now. What you see is about a 35-meter high cliff, and in front of it is a lovely tree trunk. This is your little 2-pound coin shining in the sunshine. And that tells you essentially that the last interglacial cliff can't have been more than a few tens of meters seaward of the present one, because it can only have been up to about here, because there was a forest in front of it that developed after the cliff was abandoned. Now that map might look confusing, but it's actually the same map, just with a different background. Here, the background is the 1872 OS mapping. And what it shows is up here is the last bit of the Royal Military Canal that goes all around the back of Dungeness. And there was a little appendix built in the early 1800s that was basically on the beach. Now, those little pink dots you can see everywhere here are fossil tree trunks that you could map from historic aerial photography. And you see that they overlap the cliff by, well, almost a kilometer, basically. You also have some elevation indication. You have a benchmark here from the OS, and you have the 150-foot contours. So knowing something from the history about how and this canal was constructed and its dimensions, and there's actually still bits that you can see nowadays, you can come up with a profile. This is sort of the trick point here. These are the contours, and you see there's obviously a beveled cliff at the front, at the top, and then there is a sediment-covered slope going down to basically the level and the distance of where those tree trunks start to be found from the fossil forest. And that's what I forgot about this map, is this reference here. There was a report, and someone actually dug it out before it just before it disappeared. At that point, there's a Mesolithic cave, which basically people just sauntered up the slope and then had a cave in the sandstone rocks up there, which all points to, with this profile, or the landscape that was left at the end of the last interglacial as the sea retreated back into the channel. Where exactly the rocky end was, I'm not quite sure, but that doesn't really matter at this point. So as the river rose, your beach started to arrive, preventing or protecting those freshwater habitats. And at some point, the trees died. A larger beach came in front of it. That beach got smaller, and eventually, as of the 1899 OS map, a cliff started to form and retreat started to happen again. So, conclusion for the past: cliffs in East Sussex did not retreat up to a few hundred years ago due to the presence of extensive shingle barriers well seawards of the cliffs and terrestrial habitats between them. And that is not just for the cliffs, that largely, I think, also applies to the remainder of the coastal plain. As beaches disappeared through longshore transport, cliff erosion first started in the west and reached cliff end just over the last century. And the fossil forest at Bognor, for example, disappeared quite quickly, all the other ones, because the beach cover was removed through longshore transport. And the only reason why you have this extensive fossil forest still visible at pet level is that it was uncovered the last. So the peak of the retreat rate a century ago is probably due to beach volume in front of the cliffs, which accelerates beach erosion or cliff erosion. And with a lack of beach material at the moment, there's very little erosion taking place, and hence you have this very low erosion rate. But for the whole point of looking at what happens in the future, well, historic rates of erosion do not provide a reliable data set from which to extrapolate future erosions. So that was a long way to go to get to that point. So the future will be a lot shorter. The future takes us further west to the little place of Climping. You have a much lower cliff. The land level here is about 5.5, maybe 6 meters, which is just a few meters above highest astronomical heights, but you do have chalk. You do have chalk and brick earth on top, and sometimes you have sort of clay and brick earth on top. Well, that's about what the cliff sort of looks like. Now, I can't stay away from maps. So here you see the high water mark in blue from the 1876 OS mapping. And you can see sort of the tendency to create either from initially probably natural sort of slightly harder points. You generate these lovely curved equilibrium bays, and they were then quite early on reinforced by groins, basically. What you also see is that the historic on the map mean low water line and the present mean low water line are fairly much in the same place, given that, for example, on this in this area, the shore platform is covered by sand of a few decimeters in thickness now and again, which moves back and forth. So depending on when you do your survey, that line wiggles about a little bit. And this is jumping forwards to 2016, when we still had a beach along here. There are large or different number of timber structures, groins, there's a timber breastwork, more grains, a concrete wall, and the timber structures are all from the 1970s and essentially deteriorated, and management activity that involved recharging the beach stopped in 2015 for a variety of reasons. And the yellow line is basically the cliff line from a month ago. When the erosion started in 2015, 2016, you basically had what you can see here vaguely is a flint wall from which also features on the 1870s map that had very shallow foundations, basically, some repairs with concrete, and that takes a bit longer for the sea to reduce to its constituents again. But there's also anti-tank blocks, pretty large 9-ton concrete blocks, which are actually quite handy for repairing groins. This is groin 5, just for reference, and that groin basically fell shortly after that photo was taken through outflanking and general deterioration. Now, the cliffs, as I said, they're not particularly high. They can be sort of up to 3 meters high when the beach disappears in front of them. But they basically fall when the tide's in and washes against it. They fall when the tide is just going out. They fall even when the beach has been in front of it for a few weeks or months, because it's just the release of or lack of support from the seaward side that makes them collapse. And there's, well, some winters are quite wet, and so therefore they just tumble down. Especially in clay, you sometimes get some notches forming, but this all is very, very short-lived. In places where you have the clay and at the boundary between the clay and the brick earth, you sometimes get little caves, and those caves tend to be the seedling to create actually some stacks. Here's one on clay, here's one on chalk, and you can see the lovely periglacial sort of involutions that you see also at the top of the Sussex chalk cliffs, for example. When there's lots of beach, you have a beach, and the beach actually ramps up and moves onto the land. So roll back off the beach onto the land and to the levels that it wants to. When the beach has disappeared or is very, very thin, you may see sort of some clay ramps lying around. Now, final impression, looking down the timber breastwork that you can see here. So this is the view angle. This is 2021. 3 years later, it has basically hopped 3 groin bays to groin 10, and then it really went quite quickly. Just a month later, there's basically nothing left. So changes are extremely rapid. Just something on cliff survey method. GPS with an IMU makes it a lot easier, more accurate, and slightly safer, because it can actually be sort of a meter behind the cliff. So far, there are some 35 cliff surveys being done, and I won't go into this in particularly much detail, but cliff erosion started around groin 5 in 2016, as I said, and the hard point, the updrift hard point of that bay sort of moved quite quickly to groin 4 and stayed there basically since until today. Initially, the downdrift hard point was at G6, and you can see how the bay sort of gradually started to form this equilibrium bay, and the target would have been that red crossed area line up here. Well, unfortunately, it didn't have the maturity, because groin 6, 7, and 8 failed, and the downdrift hard point switched to groin 9. So this is the target basically. And the coastline tries to sort of move towards this, but unfortunately, the area to the east has now started to invade the one from the west, and you see the last one up here, the blue line. So they two join, and the bay will be even larger in the future. The contrary is happening just to the east of it, where the downdrift hard point is actually reasonably stable, but as the timber breastwork sort of recedes, and the color coding is from between the dots and the last line that was linked to that dot. That recession basically allowed, if it was fast, not to evolve any curvature. You just get straight lines. If the hard point was in a space for a little bit longer, the curvature starts to develop, and then it just flattens out again, curves again, flattens out again. So fingers crossed this remains for a bit longer, and we can see how this larger bay form. Now, if you combine all those surveys into into slightly manageable display. So these are 5-meter segments basically all along the coastline. The average erosion rate or retreat rate is 5.8 meters. So that is somewhere between the green and the red. And then by the time you get out of the red, you get into the blue, you get into much higher annual recession rates. What can be seen is that basically, as longshore transport removed shingle along those frontages, that one started to recede first, quickly followed by this area, and then this car park area here was the last. You also see that erosion above average is really just in the first year or in the first couple of years, and then it just sort of drops again quite dramatically. You have years where erosion rates are higher than average, and you have years where it's lower than average. You have years where there's basically not much variation between sort of a longshore, or you have years where there is quite a lot of a longshore variation on a 5-meter scale basis. But the most surprising or the most astonishing is this extremely rapid erosion that takes place here. Basically, as that bay starts and that timber breastwork fails, this bit of coastline sticks out so much that erosion is, as I say, up to about 30 meters per year. But as before, it only happens at the start, and then it drops quite dramatically again. Now, there are obviously umpteen profiles, and the only thing I would like to show from here is that I said before the mean low water line didn't seem to have moved particularly in terms of from the 1870s to today. And if you measure basically if you take the elevation at 275, 325, 375, and 425 along that profile, you see that here, which is sort of above mean low water neaps, there is actually a trend of gradual lowering of the chalk in that location of about 11 centimeters per year. But the further you go out, there's basically nothing in terms of a trend, although the trend might be masked because, as I said, there's variability between this being surveyed as just the geology or something which has sand on top. And that is one of the biggest difficulty in analyzing these profiles. I worked out in the end is that you can't tell from the profiles whether that slope here is a thin beach or is the actual geology. Now, finally, those 5 lines are basically the lines along, or the elevation along the cliff. 4.5 and 5 in terms of distance away from an artificial starting point of the profile represent the cliff, and 4, 3, and 2 are, I thought, representative of the beach or the foreshore in front, which would have an impact on protecting that cliff face, for example. Now, that is actually really difficult to establish. As I said, I don't know whether it is beach or whether it is geology. The cliff surveys are not timed with the normal surveys of the beach. They're done by different people, basically. But what you can see is up here is a measure of wave impact, and that is a simple water level plus half the wave breaking wave height. And you see that there obviously erosion takes place in the winter when the energy is high, especially when you have erosion starting. But the link between what the beach is doing in front is really difficult to see. You can see it for individual ones. So here, because the retreat is very narrowly defined in terms of timing, and the survey of the beach just happened afterwards. So if you assume that the beach had been at that level before, then obviously it's not a very large distance in front of the cliff, so therefore it would have been ideal for the cliff to being attacked. But overall, this well, or it needs more work, but I haven't yet found a particular pattern in that. So jumping to the last penultimate slide, the future. So if data doesn't necessarily tell you much about going forward, although it may, because there's now a lot of data for calibration, what have people so far attempted? So the red line is basically from where the cliff started. We had a geomorphological expert panel in 2019, and they individually, after a day of deliberation, each one drew a line for where they thought the coastline would be in green on that map. Yellow, as I said, is the last survey, and this is actually last week. There's also in 2018, a consultant ran an escape model, and they predicted for 50 years in the future. And you see something's not quite right, because the 50-year lines are basically in line with the 10-year lines of the expert panels. And when you look at where the yellow line is at the moment, I basically think that the expert panels were not that bad. There's another 4 years to go. And I reckon the yellow line will be somewhere within that envelope of the green lines. And then obviously we have the official National Coastal Erosion Risk Mapping that provides a value here in the sort of white dotted area for 2025. And that suggests even less erosion taking place. Here at this location, actually the actual erosion is already outside of that under present emissions scenario. And we didn't even have any sea level rise really in the last 6 years. So future erosion rates, when? Where are we with this uncertainty graph? Well, it's great. We have a little bit more certainty in terms of the past in here, which is great, but that doesn't really help an awful lot with the future. So the lesson after 50 minutes is extrapolation. Well, you can extrapolate anything, but obviously the data presented here is you don't really know which value you want to extrapolate. So therefore, extrapolation is probably the least certain method going forward. A process model like SCAPE, for example, I just grade this out because it might actually be quite good if you feed it some calibration data, which obviously in 2018, when the cliff line had just sort of started to erode, wasn't really available. At the moment, the best shot seemed to be something like a conceptual model or expert geomorphological assessment. At least that's what the data shows, or and that might be the real reason, these for experts were just lucky. So thank you very much.
Brilliant. Thank you, Uwe. That was fascinating and very thought-provoking as ever. I'm going to allow everyone to unmute themselves and come off camera so that we can have a few minutes for questions. So if you'd like to, if you have a question for Uwe, you'd like to put your hand up, please do so. Equally, you can put questions in the chat. Cherith, you're first up.
Hello, Uwe. Sorry, you can't see me, but nice to see you. And thank you for a very interesting talk. It's I was reading your paper on the general lack of erosion on the Sussex coast with interest recently. I wondered what you think about the view that a cliff is a cliff is a cliff, regardless of its setting, and that they are self-organizing systems whereby the collapse begins with a multitude of smaller collapses, and you end up eventually with a larger collapse, and that in fact the answer to predicting future cliff retreat might lie in power law scaling.
I think I saw that paper. I don't think I
There's
understood.
quite a few papers on it.
Yeah, and I don't think I understood what it meant. I think because there are so many processes that can go on, how you combine them into something is well, I don't know what is the best option, and I think there is obviously the whole debate as to whether you need undercutting or not, or each cliff is different, as you say. Cliffs in Norfolk are completely different from, I think at least, the chalk cliffs of Sussex. I think the biggest difficulty is, in terms of predicting cliff erosion, that you have very little to go by to calibrate whatever model you have.
Indeed. I thought it was fascinating seeing your slide towards the end where you showed potential future cliff positions. And I thought, oh, you know, if you've got some wizzo who can do power law scaling, it would be interesting to see what they come up with for that site. Needless to say, I am not the wizzo.
I mean, the data is for everyone to have.
Yeah, no, really interesting. Thank you.
Good.
Jareth, good question. Does anybody else have any questions they'd like to ask Uwe? See anything in the chat either? If not, I'll use chair's prerogative.
Hello.
Steve.
I'm sorry, you can't see me either. Just a quick one then, if nobody else is asking. Did you record, or did you attempt to record, the actual conceptual model that people were applying when they did their EGA assessment? Did you sort of attempt to say what is it you're modelling here to come up with your answer?
No, I think it was this sort of very mushy, muddled preconceptions they brought into the meeting, and then sort of discussing for 6 or whatever hours what has happened in the past and so on, and then everybody drew their line. So it's probably a more intrinsic model than something that you can necessarily put on paper. But the thing like the equilibrium bay works perfectly fine. I mean, the development always tends to go towards it. Although what I find is, and I didn't have the time for that while the landward move is quite fast, the equilibrium bay says that you have erosion quite a distance in the lee of the hard point, and that doesn't seem to happen because once you get a little bit of a bay forming, you get in that corner quite a lot of beach, and so A, it's sheltered, and B, you have a beach. So the development towards this full bay is probably very, very slow at that end around the hard point.
Hello. Can I ask a question?
Go ahead,
Yes,
Jim.
sure.
Yeah. I thought that was absolutely fascinating, really top quality. The question I want to ask refers locally to the area you've studied, and it relates also to France as well. And that is the source of the flints, because the question I want to ask is, as I understand it, those flints were created from the erosion of the English Channel during marine ice stage 12, when the channel was breached and the barrier was created between France and England, and that was the flint was washed out, and that accounts, as I understood it, for the abundance of flint in Dungeness and again on this opposite side of the channel. Now, if that's the case, would that affect your interpretation? Because it would produce an abundance of flint because there was an abundance of chalk there. And I wonder what you think about this.
I mean, there's this seminal paper about the abrasion of flint on the beach. So obviously the flint is not there forever. It sort of grinds itself down. So if it comes from marine isotope stage 12 or so, that obviously had a long period of time to just rub around. I don't think it changes the interpretation, but I do actually not think that is necessarily the case. I mean, whether there was the chalk is still there. The chalk is still forming large parts of the surface of the English Channel, and obviously there's lots of shingle that sits in old channels. So it's not all at the surface. The true volume of how much shingle or gravel there is on the coast would be quite interesting.
But if you consider the amount of chalk that was removed between Britain and France, between England and France, then there's far more than you are removing from along the present day cliff lines in the area, or the recent cliff lines in the area, or the last cliff lines.
But if you think about the sort of violent breaching of the land bridge between Dover and Calais, for example, then you might have generated a very strong flow that removed quite a lot of that gravel further west out onto the shelf, or I don't know how far it would go. But I haven't thought about that one as well. No.
The final point, just making, is that is the area where the flint is concentrated, just as it were downstream of the channel breach, and it's both sides of the channel. So that was the point. But anyhow, I don't have an axe to grind, and I really appreciated your study. So thank you. Thanks very much.
Thank you. Thanks.
Thank you, Jim. An excellent question. Maybe an idea for some more thinking and more work over in the future.
Yeah.
Just before we finish, the final question has come in on the chat from Lucas, who asks, how does the 5.8 meters per year average compare to other averages, and can it be used as a predictor?
Well, it's an average around a very large fluctuation. So with a tail towards the much more rapid, as I said, that there's plenty of parts that have gone at 25 to 30 meters per year. I would never apply this to anywhere else than this site, unless you have something that is really very similar. I wouldn't really use that. I don't know exactly how much the rate, for example, at Haysborough was or something, but it's a different setting. Yeah, I wouldn't.
Okay, great. Thank you, Uwe. Right, I think we're just about out of time. So what I'm going to do is just mention next month's seminar, which we hope you will all sign up to. The details haven't come around yet, but I think the hope is it's going to be Mark Lee talking about geohazard risk to desert pipelines, or something entirely different, which rather shows the nice breadth of these seminars, I think. So with that, big thank you, Uwe, for a fascinating talk. I found it really thought-provoking. I hope you all did too. And a big thank you to all of you for joining. Please keep an eye out, as I say, for comes around future seminars. And if you have topics you'd like to put forward, either yourself as a speaker or that you'd like to hear others speak about, you'd like to recommend potential speakers, please get in touch with someone on the committee. So either myself, Nish, Hannah, or any others if you've got contacts on that committee. And with that, I'll say thank you very much and have a good rest of your day.